Howdy! In this video, we are going to cover the big O notation and basically review that topic. So let us jump right into it. Okay, so what is big O notation? Big O notation is basically a way to represent an algorithm's worst case complexity. And we use big O notation for asymptotic upper bounds, which means we use basically big O notation when we're talking about large input values. And so this slide basically talks about the intuition and formal definition of big O notation. So for example, um, if you have f of n is equal to 100n and g of n is equal to n squared, then eventually g of n will grow larger than f of n, and thus 100n is equal to big O of n squared. But note that since the definition says that since the definition says some multiple of g, we can also say that 100n is equal to big O of n, because 100n is less than 101 n for positive values of n basically. And so here's a more formal definition of big O notation. So if f of x and g of x are functions on real numbers, then we say that f of x is equal to big O of g of x if there exists some constants x sub 0 and c such that the absolute value of f of x is less than or equal to c times the absolute value of g of x for all values of x greater than x sub 0. Okay, so um, one question which comes to my mind when I like solve big O problems is that why do we always try to find like tighter big O bounds? So for example, in this case, we could have stopped over here and just said that 100n is equal to big O of n squared. But why do we always try to like find a more tighter bound? So the reason for this is that it basically helps us to understand, analyze, and compare algorithms. So for example, if you have $10 in your pocket and you go up to a friend, and if you don't want to tell them how much money you have, and if you say that I have an amount of money in my pocket and I guarantee that it's not more than $1 million, then in this example, your friend basically it doesn't really help your friend to know that the amount in your pocket is not more than $1 million, because for example, if you're going to a restaurant, you can't pick which restaurant to go to if you don't have like a more tighter bound. So basically that's the reason why we always try to find a tighter bound for big O notation. Okay, so this slide basically has this table which covers the order of complexity of different functions. So as you all can see, um, a algorithm which runs in constant time, which is represented by big O of one time complexity, is considered to be like the fastest algorithm, and then that is followed by logarithmic algorithms, and then linear, n log n, quadratic, cubic, exponential, and then finally factorial. Okay, so here I'm basically trying to give examples of like basic arithmetic using big O notation. So for example, if you have an algorithm which works or which runs in n cube plus n squared plus n plus 1 time, then you can basically simplify this and say that the algorithm is of big O of n cube time complexity, because n cube is basically dominating over n square, n and 1. And so basically big O of n cubed plus n squared plus n plus 1 is equal to big O of n cubed. And then the second example basically demonstrates that if you basically find, like for example in this case, the fifth power of log n, then log n is still considered to be faster than like big O of n time complexity algorithms. So basically, again in this case, n dominates over log n to the fifth power, and so big O of n plus log n to the fifth power is equal to big O of n again. And then the third example over here demonstrates that even if you change the basis of log, it still doesn't change the time complexity. So for example, log n base 7, so big O of log n base 7 is the same as big O of log n base 5, and so on. And then the last two algorithms, or the last two examples over here, basically again demonstrate something similar to the first example, that n factorial dominates over 2 to the n and n log n dominates over n. And so we get big O of n factorial plus big O of 2 to the n is equal to big O of n factorial, and big O of n log n plus big O of n is equal to big O of n log n. Okay, so the next 2 or 3 slides over here are basically some extra information which is like good to know, because like one question that arises in our minds is that why is big O of 2 to the n better than n factorial, or like basically how do you construct this table, or how do you know that a particular function dominates over the other function. So a very easy way to find this is by using some basic calculus. And so on this page, I've given an example of big O of log n to the second power versus big O of n. And so basically what I did is I found limit n tends to infinity of the first function over second function. And depending on what this value um, comes out to be, we can basically conclude which of the two functions dominates over the other one. So for example, in this case, we got uh, limit of n tends to infinity of log n to the second power over n is 0. And so basically we can conclude that the function in the denominator is basically dominating over the function in the numerator. And so basically n dominates over log n to the second power. And conversely, if the fraction tended to infinity as n tends to infinity, then we would have concluded that the function in the numerator dominates over the function in the denominator. And similarly, if the fraction tends to a non-zero constant, then in that case we can conclude that both the numerator and the denominator functions are like equivalent to each other, so they're like almost the same as each other. And similarly, for big O of 2 to the n versus big O of n factorial, I again um, we basically will share this PowerPoint presentation with you, and then you can basically look into this PDF file which has the proof for this particular example as well. And if you have like similar questions, feel free to email them to me, and so I'll try to update this PDF with answers to those questions as well. Okay, so for now let us jump right back into like examples. And so our first example over here is basically a for loop. And so we basically have like we are basically declaring count to be 0, and then we have a for loop which goes from 0, 1, 2 all the way up to n minus 1, and then we increment count in every iteration. So basically the running time function in this case comes out to be 2n plus 1, because so count plus plus is basically two operations. The first one is so you can think of this as count equals to count plus 1, where count plus 1 is basically incrementing count by 1. So that's like one operation, and then assigning that value to count is the second operation. So and this loop basically iterates n times because it goes from 0 all the way up to n minus 1. So that's where we get 2n plus 2n from, and then the plus 1 comes from the initial declaration of count to 0. And so the time complexity of this algorithm comes out to be big O of n. Okay, so for example 2, we have a similar problem, but in this case we have two for loops, and so these are like nested for loops. So as you can see, we first initialize count to 0, and then we have an iteration variable I which goes from 0, 1, 2 all the way up to n minus 1, and then we increment the variable count, and then we have the second for loop where the iteration variable j goes from 0 all the way up to m minus 1 and gets incremented by 1 every time. And so the running time function for this particular example comes out to be 2 times mn plus 2 times n plus 1, because so basically the inner for loop iterates m times, and then the outer for loop iterates n times, and so this particular line is basically 2 mn operations, and then the count plus plus line over here basically is again two operations for n iterations. So that brings the 2n in this equation, and the plus 1 comes from the initial declaration of count to 0. And so we can say that this example has um, bigger time complexity of mn. Okay, so here's the third example. In this case, we're again initializing count to 0, and then we have nested for loops. But the difference in this example is that the inner for loop is basically dependent on the outer for loop. So basically j goes from 0 all the way up to I minus 1. And so yeah, so first, when in the first iteration of the outer loop, when I is equal to 0, um, this for loop wouldn't run, because basically 0 is not less than 0. And then when I equals to 1, this inner for loop basically iterates one time. And then when I equals to 2, this inner for loop will iterate two times when j is 0 and 1. And then it will keep iterating until I equals to n minus 1. And in that case, basically, we'll again have n minus 1 iterations of this inner for loop. And so the way we find the running time function in this case is by using this formula right here, which says that the sum of first n natural numbers is equal to n times n plus 1 over 2. So in our case, it's 0 plus 1 plus 2 all the way up to n minus 1. So this is basically the same as the sum of first n minus 1 natural numbers instead of n natural numbers over here. So we substitute n minus 1 in this equation instead of n. So we get n minus 1 multiplied by n minus 1 plus 1 divided by 2. And so that comes out to be n minus 1 times n over 2. So that's basically the number of iterations of the inner for loop. And so basically for every iteration we have again two operations on this line. So basically count is first incremented by 1, and then that value is again assigned to the variable count. So basically the running time function of this example is n minus 1 times n plus 1. And the bigger time complexity of this example comes out to be um, big O of n squared, because when we simplify this, we'll get uh, n squared minus n plus 1. So big O of n squared minus n plus 1 comes out to be big O of n squared again. Okay, so for example 4, we basically have a for loop which keeps running um, until n is greater, or which keeps running while n is greater than 0. So and for every iteration it basically divides the value of n by 5. Note that this is integer division. So if you take for example 26, then 26 divided by 5 would give us 5, and so it won't basically would like remove the remainder. And yeah, so in order to find the running time function of this example, what we'll do is we'll take a couple of examples. So we'll basically run this algorithm when n is equal to 25, for example. So the reason I chose 25 and 26 is because 25 is basically actual power of 5. So 25 is 5 to the power of 2. And then 26 is basically adding 1 to 25. And so when n is equal to 25, this loop basically iterates 3 times. So in the first iteration n is equal to 25, and then in the second iteration n is equal to 5, and then in the third iteration n becomes 1, and then finally when you divide 1 by 5 you get 0. And so this loop will basically break in that condition. And similarly for n equals to 26, we get again 3 iterations, because n equals to 26, and then 26 divided by 5 would give us 5, and then 5 divided by 5 would give us 1, and then 0. So it's basically again three iterations of the while loop. And for every iteration we again have two operations, because n divided by equals to 5 basically means that you're first dividing n by 5 and then assigning that value back into n. And so the running time function in this case comes out to be 2 times of the floor function of log n base 5 plus 1. So if you notice over here, in the case that n is equal to 25, we get 3 iterations, and n equals to 26 again gives us 3 iterations. So and 25 is basically 5 to the power of 2, and so 25 and 26 give us the same iterations. And so basically the reason we add 1 is because we have an extra iteration when n is equal to 1, which we don't consider when in log n base 5. And so the big O time complexity of this example comes out to be big O of log n. Notice that we ignored the base over here, just like we saw in the previous slides, and so we just changed the base back to 2. Okay, so for example 5, we again have two nested for loops. And so we first initialize count to 0, and then the outer for loop basically has an iteration variable I, which goes from 0 to n minus 1, and then the inner for loop basically has an iteration variable j, which goes from from 1 all the way until it is less than, or yeah, so until it's less than m. And so we don't exactly know the number of iterations, but the way we'll find this um, is by taking some examples. So let us take m is equal to 32, which is 2 to the 5. So in this case, we'll get that j would be first equal to 1 in the first iteration, then 2 in the second one, then 3, 4, and then 5. And then 2, 4, 8, and then 16 in the fifth iteration. And then in the sixth iteration, when j equals to 32, this loop will basically break because 32 is not less than 32. But when we take m equals to 33, we'll notice that j goes from 1 to 2, then 4, 8, 16, and then it also iterates when j equals to 32, because 32 would in this case be less than 33. And so basically what this implies is that the inner for loop has the ceiling function of log m iterations, um, because in the case of 33 there were like 6 iterations, while in the case of 32 we got just 5 iterations. So basically the running time of this example again comes out to be 2 times n multiplied by the ceiling function of log m plus 1. And the bigger time complexity of this example is big O of n log m. Okay, so example 6 over here is pretty much similar to example 5. The only difference over here is that we have an equal to sign over here. So if you look at example 5, there's no equal to sign over here, but this small change basically changes our answer. And so if in this case, if we check for m equals to 32, we'll see that j will iterate basically like this inner for loop basically iterates 6 times. So j equals to 1, and then 2, 4, 8, 16, and then 32. And then when m equals to 33, it again iterates 6 times. So 1, 2, 4, 8, 16, and finally 32. So what this changes in our answer is that basically the number of iterations of the inner loop in this case are the floor function of log m plus 1. So this is basically pure observation. So like once you like start observing that the number of iterations in this case is the same as the number of iterations in the case when m equals to 32 is the same as m equals to 33, you'll realize that um, it's basically equal to the number of or that's basically equal to the floor function of log m plus 1. And so the running time function in this case is 2 times n multiplied by the floor function of log m plus 1, and then the plus 1 comes again from the initialization over here. And so there's n iterations of the outer for loop, and then floor function of log m plus 1 iterations of the inner for loop, and then this line is again 2 operations per iteration. So yeah, so basically the big O time complexity of this example comes out to be big O of n log m again. Okay, so for example 7, this is again very similar to example 5 and 6. Notice that the only difference in this case is that we started j from 0 and not 1, and so the reason that this is important is because in this case we end up with an infinite loop, because when you multiply 0 by 2 you get 0, and then you again get 0, then you keep going. And so basically make sure that you look closely at the bounds inside the loop, because it is very important to basically check the starting and the ending values. And in order to do this, it's very good if you could like try you should basically try writing the values of the iteration variable until you see the pattern, and so that would basically help you reduce some like um, like mistakes like this in problems where you're trying to be more tricky. And so the runtime function in this case basically doesn't exist. It's like infinity. And yeah, so here's example 8. So basically in example 8 we have an if-else statement which basically takes us to two different loops. So the first loop over here is basically a loop which runs in log n time, just like we saw in previous examples. And this loop right here basically runs in linear time. So basically the main thing we need to understand is that whenever uh, there is an if statement, we'll always, or not only if statement but like any other conditional statement, we'll always try to find the worst case time complexity. So in this case it's log n versus linear time, and so the time complexity in this case would be big O of n, because uh, this this loop right here, this for loop, basically um, is the worst case of our algorithm. Okay, so for example 9, we basically have been given a function foo1 which takes in input as like an integer. So it basically takes the input in the form of an integer k, and then uh, we have been told to assume that the function foo1 basically um, does log k operations. And then we have a for loop um, where the iteration variable I runs from 1 all the way up to n, and it gets incremented by 1 in every iteration. So basically um, for every value of I will again run the foo1 function. And so okay, so one important um, math formula we need to understand or like use in this problem is log a plus log b is equal to log a times b. So for the first iteration when I is equal to 1, basically there's a log 1 operations, right? So there's log 1 operations for the first iteration when I equals to 1, and then log 2 basically log 2 operations for I equals to 2, and then log 3 for I equals to 3, and then all the way up to log n for I equals to n. And so basically whenever we try to simplify this, we basically, so we're always trying to analyze the worst case time complexity, right? So we'll basically say that log 1 plus log 2 plus all the way up to log n is equal to or is less than or equal to log n plus log n plus all the way up to log n. So basically n times log n. And so we get the big O notation for, or big O time complexity for this example to be big O of n log n. Okay, and for example 10, this is slightly tricky. So basically we have a while loop and then we have a for loop inside it. and then notice that we basically initialize a variable I to n, and then another variable count to 0, and then we have a while loop, and then we have a for loop inside it, and then at the end of the for loop we'll basically divide I by 2. So I'll go from n to n by 2 to n by 4, and then all the way up to like 1 or 0. And the inner for loop basically depends on I. So in the first iteration, basically it would, when I is equal to n, it would go from j equals to 1, 2, 3 all the way up to n. And then when I equals to n over 2, it goes from 1, 2, 3 all the way up to n over 2, and then so on. And then count plus plus is again two operations, as we just saw in the previous examples. And so, okay, so the way we'll find the number of iterations in this case is by using the formula for a geometrical series. So basically, when I equals to n, there's n iterations, and then I equals to n by 2, we again have n by 2 iterations, and then so on. So basically, as n tends to infinity, um, as we already know, like Big O notation is basically trying to find the time complexity for large values of n, or large inputs basically. So as n tends to infinity, we'll get that n plus n by 2 plus n by 4, so all the way. So this series will become longer and longer. So it could grow all the way up to like 100 values, or like 500 values, or like even longer than that. And so the way we basically find the number of iterations is we use the geometrical series formula, which basically gives us an approximation of the number of iterations. So n plus n by 2 plus n by 4 plus all the way up to like 0 would basically be n divided by 1 minus half. And so that basically gives us 2n iterations. So what this means is that we have 2n iterations of the inner loop. And so for every iteration, we again have like two operations on this line, because you're first incrementing count by 1 and then assigning that value to count. And so basically our running time function comes out to be 2 times 2n because of this, plus 2 times of the floor function of log n plus 1, which comes from this while loop over here. This is exactly similar to our previous question. And then plus 1, which comes from here, and then the last plus 1 comes from int I equals to n. And so the big O time complexity of this example comes out to be big O of n again, because n obviously dominates over log n. And so yeah, that's it for this videos. Here are some sources which I used for creating this presentation. So if you're interested in going through them, I have the links of all of those websites attached over here. And good luck for your exams. Thank you.